let's get started. So if you're just coming in, we're going over these do now questions. It's a little bit of a review from last time. We're not reviewing everything because we can't, but we're going over a few things that are relevant to what we're doing for Chapter 2. So question number 1. Is the measurement 16.70 milliliters a length, volume, or mass? And put your answer in the chat. Right, we're starting with an easy warm-up. It's a volume. You can look at the units, they're milliliters. Anything with the liter tells you it's a volume. How many significant figures are in 16.70 milliliters? Most people said 4 sig figs, which is the correct answer here. Remember that when you see a decimal, that means that any 0 that's at the end of the number is measured. So it's going to be included in sig figs. You see a decimal, all the zeros count. Number 3, write 16.70 milliliters in scientific notation. How would we do that? Exactly. We need a coefficient that is, well, almost exactly. We said that all of these numbers are significant. So our coefficient is 1.670. Don't forget the 0 here because it is significant. Then you say, all right, I move my decimal point 1 time, so we put a 1, and the number is bigger than 1, so the exponent is going to be positive. You also don't want to forget your units. So include all of the significant figures in the coefficient for the scientific notation. We good on that? That's just a little refresher. But for the most part, y'all got it. It's just a couple little details. Yes. We can go over that again. So we're looking at the number itself that we're trying to write in scientific notation. So we're taking 16.70. If your number is bigger than 1, then that means that your exponent is going to be positive. If the number that you're trying to write in scientific notation is less than 1, so we're talking about a decimal, then your exponent is going to be negative. So if I had 0.1670, then it would be 1.670 times 10 to the minus 1. Is that more clear? Great. Other questions, or let me know you're good and you're ready to move on. so you can think about it that way too. So if you move your decimal point, when you're making your coefficient, if you move your decimal to the left, then that means you're going to have a positive exponent. And the opposite is true if you move the decimal point to the right. So it's just two ways to say the same thing. I think that it's a little bit clearer to look at the number itself and say, okay, it's bigger than 1, so the exponent needs to be positive. But whatever floats your boat. Other questions, or let me know that we're good? All right, we got one vote for good. Blackboard might be a little bit slow right now. It's kind of acting up. Okay. So we're going to move on to Chapter 2. Chapter 2 is big, a little bit of a beast, because it's like all math. And if you don't like math, this won't be fun. But we're going to make it as fun as possible. Okay? So what we're going to do is we're going to go through some practice problems, starting with some of the easier stuff. So we talked about physical quantities, the basic units, and their symbols in the beginning of the Chapter 2 lecture that was posted on YouTube. What I want you to do is try to fill in these blanks. So make this chart. It's literally a chart that I took from the PowerPoint. Okay, fill in the places that are blank, and this will be a really good reference chart for you as you go through and do your work. So I'll give you 2 minutes to write it out and fill it out in your notebook. I'm going to start slowly filling these in. If the basic unit is a meter, we're talking about a length. And the symbol for meter is a lowercase m. If we're dealing with volume, the basic unit is the liter. Its symbol is a capital L. G corresponds to the unit of grams. And that means we're dealing with math. And finally, time, the base unit that we're using for that is the second. And its symbol is an S. So that's not really a concept, that's just something that you need to know. So if we're talking about any one of these different quantities, you need to know what units you should be reporting your answer in. Yes. Yes, there is, but you don't need to know that for this class. That's a physics question. So we can put a slash here and say weight. You'll see both of them in word problems. Other questions? Otherwise, you can tell me that we're good or give me that thumbs up and we can move on. So a little gentle, gentle ease our way in. All right. Building up that confidence. So let's go. This is the metric prefixes table. If you do not already have it, you need to put it into your notebook. Is there a question or was that a... Yeah. So there's you can look at the PDF online on Blackboard. So the lecture notes, it's in the PDF there. So you can print that off. Otherwise, if you have access to the textbook, you can look at it there. Or if you have it online, like the e-text, you can look at it there. I tried to put it in the places that we're going to use it, but you will not need to memorize this for the exam. You will be provided with this exact table, except for the arrows. You're welcome. So I wanted to take a minute to go over the information that's in this table. So we have the prefix itself, right? So what you would be writing if you were writing it out. Then we have the symbol, and then the multiple or the fraction. So let's go with something that we are already sort of familiar with and walk through the table. Let's talk about centi. We compare that with meter for centimeter, cm. That's the prefix, the C. The M is the meter, and that's our basic unit. What centimeter means is that I have less than 1 full meter. What I actually have is 0.01 meters, or 1/100th of a meter. That's how you can read this chart. You're also provided with the scientific notation, which you'll see as we're doing problems. Sometimes it is more helpful to put the scientific notation than the decimal because it helps you to kind of, if you need to write your answer in scientific notation, oftentimes that helps you get there a little bit faster. But either way, that's how you read the chart. So if I were to say, let's look at kilo, and I had a kilometer, how many meters would I have? Because kilo is one that increases the value of that meter. So looking at the chart, how many meters would I have? You can put that in the chat. Yes, you'd have 1,000. You would have 1,000 meters. So that's how you can read this chart. We need to read this because we have to be able to write what's called unit equations. Remember that unit equations, they just define a relationship. So we're not really doing any kind of math per se. We're just saying if I have 1 kilometer, it's the same thing as saying I have 1,000 meters. That's all we're doing. So we're defining a relationship between two units. You also want to remember that unit equations have an equal sign. When you're telling the difference between unit equations and unit factors, that will come in handy. Unit equation, equal sign. I'm going to go through the first one. Actually, we sort of already did go through the first one, but we'll go through it again to write a unit equation. And we'll just write it in a slightly different way. So for number one, we're looking at the relationship between a centimeter and a meter. If I have 1 centimeter, how many meters do I have? That's one way of setting up a unit equation. Yes, I wasn't even asking for the answer, but yes, that's the answer. So let's figure out how we get there. So you can look at the table and say, oh, okay, I have a centimeter is equal to 0.01 meters, right? The other way to do that is to figure out, okay, centimeter, is that bigger or smaller than a meter? A centimeter is a smaller unit, so we're going to call that one small. And we're trying to go to a different unit, the meter, which is bigger. Now, I told you about the scientific notation over here and how sometimes that's a little bit more useful. Because if we were doing femtometer, you're not going to want to write out all those zeros, okay? You're going to want to use scientific notation. But just pulling it directly from the chart, the sign of the exponent, that little guy right there, may not be right. So if you're going from a small unit to a big unit, the exponent that you're going to use for that big unit is going to be negative. So you take just the number value from the chart, that's 1 times 10 to the 2, and then you say I'm going from a smaller unit to a bigger unit, so I need to put a negative sign in front of my exponent. And you don't forget your units. I'll do number 2 as well because that's an example of going in the opposite direction. Do I need to go through and repeat this, or can I go and do number 2 as well? We have a vote for repeat it. Okay, so let's walk through that again. I'm going to use a different color just in case I write something else. So we're starting with saying, if I have a centimeter, how many meters do I have? You can look at the chart directly and figure that out. You have 0.01 meters. But let's say that it wasn't that easy, or you wanted to be able to write it in scientific notation, and you want to make sure that you're writing the correct sign for your exponent. Centimeter is smaller than a meter. So if I have centimeters, you can think about that as being like the slice of pizza, right? Versus the meter being the whole pizza. I can have 8 slices of pizza, but in terms of number of whole pizzas, I've only got 1. So centimeters are smaller than a meter. That means I'm trying to go from a small unit to a big unit. Whenever you're doing that, when you're writing your scientific notation, your exponent is going to be negative because you're writing your unit in terms of a bigger unit. So if I say had 5 slices of pizza, when I went to write that in terms of whole pizzas, I'm writing a fraction or a decimal. It's the same thing with going from a small unit, like saying I have 1 centimeter. How many meters do I have? I'm going from 1 to a number that's less than 1 because I've got a bigger unit. So we're going to say 1 centimeter is equal to 1 times 10 to the minus 2 meters. Now I think that if we do the second question, it might help make that method make a little bit more sense. So if you don't mind, I'm going to do that one and talk it through the same way. And then if there's still question marks over your head, then we'll go through it again. This time we have the kilometer, or not a kilometer, a kiloliter and liter. So if I have 1 kiloliter, how many liters do I have? Now, if you have the table and you know your prefixes, you may just know it right off the top of your head. But you may not know. So I assign big versus small to help me figure out what I'm doing and what my number should be. I know that kilo is big. It's going to make my number big. And it's bigger than a regular liter. So when I write the number of liters that I have, it's going to be a bigger number than the 1 that I have for kiloliter. So my exponent, when writing in scientific notation, is going to be positive. Then I go to the table, I find the number, 1 times 10 to the third liters, and our exponent is already positive, so we don't have to do anything. So we're going from kiloliter, which is a bigger unit, to the liter, a smaller unit. It makes sense that we're going to have more liters when we're writing just the pure number than kiloliters. Do I need to repeat it, or is it making more sense? Okay. Now it's your turn. That was a trap. I'm tired of doing the work. It's your turn. So I want you to do number 3. You have nanograms and grams. Write a unit equation to describe that relationship. I'll give you 2 minutes to do that. How are we doing? Do we need more time? Otherwise, you can put your answer in the chat. It looks like we're getting it. So if I have 1 nanogram, yes, there's a hand. Yep, exactly. So we've got our basic unit in the middle. Anything that is above the basic unit with the prefixes is going to be bigger than the basic unit. Anything below is going to be smaller. And it's the same thing if you're comparing, let's say, giga something versus kilo something. Giga is higher up, so that one's going to be big, and kilo is going to be small. So it's a comparison. Is that more clear? Okay. You're welcome. So we have 1 nanogram. We're trying to figure out how many grams we have. Nanograms are down here. Grams, we're talking about the basic unit. So nanograms is smaller. We said that our rule is that if we're going from a small unit to a big unit, we're going to have a negative exponent. So we look at the chart just for the number, and then we put in that negative. Now, here's a bonus. You can also do this by saying, I have 1 gram. How many nanograms do I have? In this case, gram is bigger still, so we're going from big to small. We still need our number, that exponent from the chart. But in this case, our exponent's going to be positive because a gram is bigger than a nanogram. So we're going to have more than 1 nanogram to have 1 gram. So you take the same exponent, the 9 from the chart, but instead of it being negative, it's now positive. These 2 unit equations say the same thing. So there's 2 ways to write it. I just always choose to put a 1 in front of the first one because to me that's just easier. But whichever way makes the most sense to you, that's how you write it out. And you'll see as we do problems, it doesn't matter as long as the unit equation is correct with relating the 2 units. Do we need to do some more practice with those, or can we move on? I see a hand raised. No, it's relative. So if you're saying I have 1 gram, how many grams do I have? It's the same. I have 1 gram. It's always going to be one is bigger than the other. So you look at the chart and see which one is the closest to the top. That's the one that you label big. The other one is small. If you choose to use this method. Okay? Cool. All right, so we got a few people saying move on. So we're going to move on. I had this for just in case we need to do some more. Now we're going to write unit factors. Unit factors look like fractions. So for this first unit equation, and I'm going to keep labeling these because you need to know the terminology. If I ask you for a unit equation, it needs to have an equal sign. If I ask for a unit factor, it needs to look like a fraction. You're literally going to take the values from your unit equation and write it as a fraction. So you replace that equal sign with a line for your fraction. Then you can flip it over. So what's in the bottom, or the denominator, you put in the top, which is the numerator, and vice versa. So you should always be able to get 2 unit factors for every unit equation. So unit factors, I will abbreviate UF. Unit equations, UE. 2 unit factors for every unit equation. So go ahead and write 2 unit factors for this unit equation for kiloliters and liters. Yep, we have an answer that looks good. It's probably taking longer to write it out in the chat than it is to write it out by hand in your notebook. But I feel like writing out the unit factors is the easy part. It's getting to the unit equation that can be problematic. So those are the 2 that you should have. 1 kiloliter over 1,000 liters, and then you flip it. 1,000 liters over 1 kiloliter. So unless someone says otherwise, I'm going to say that we can keep going. We're going to have more practice with writing unit equations and unit factors when we do these conversion problems. So if writing the unit equations is still a little bit shaky for you, that's okay, because you're going to get more practice as we go along. So we good to move on? Okay. And writing out the unit factors in the chat, that's tight. But thank you. Thank you for doing it. So let's try our hand at one of these metric conversions. You're performing an experiment that requires you to measure 56 milligrams of sodium bicarbonate, which is just baking soda. Your balance reports mass in grams. How many grams of sodium bicarb do you need? Report your answer in scientific notation. So I'm going to walk through this one and ask you guys questions along the way. And we'll set up a method, the same method that I used in the lecture video, but we're going to kind of do it together versus you just watching me. So the first thing you always want to do is rewrite your question. There's a lot of words up there. Let's make it plain. We have 56 milligrams that we need to measure out. Since the scale doesn't read in milligrams, it reads in grams, we need to know what number we're looking for. So how many grams should we measure out? That's the question. From here, we know what our unit equation needs to be. we need to somehow relate milligrams to grams. Is a milligram bigger than a gram or smaller than a gram? It's smaller. So we're going to label this one small and the gram as big. So when we're writing out our unit equation, we're going from small to big, which means for our big exponent, is it going to be positive or is it going to be negative? Right, it's going to be negative. So that's our unit equation. From there, we can write out two unit factors. And those are our fractions. I'm about to write the same thing twice. Y'all, I taught a class literally right before this one. So my brain might be a little bit more fried than usual, but I'm going to try to keep it together. So those are our two unit factors. I'm going to label them A and B. The last part that we have to do before we still haven't touched our calculator is set up your calculation. We're starting with 56 milligrams, and that we just got from the problem. But now we have a decision to make. We need to use one of these unit factors to get us from milligrams to grams. That means that we have to choose the unit factor that's going to let us cancel out the milligrams and leave us with grams. If 56 milligrams is in the numerator or the top, where do we need to have milligrams, the top or the bottom, for it to cancel out? Yeah, we've got to use B. We need those milligrams in the bottom. So that means we're going to choose B. You need to fill in all of your numbers from the unit factor. The last step before you touch your calculator is to make sure that your units are going to cancel. Now this is going to matter even more when we use more than one unit factor. For right now, it's pretty simple. You can see that the milligrams cancel, you're left with grams. So why don't you go ahead and do that calculation for me and try putting it into your calculator using the scientific notation. 1 times 10 to the minus third. Okay. So you're multiplying 56 by 1 times 10 to the minus third. You can put your answer in the chat. Y'all are on it. So your calculator is going to tell you 0.056. But let's revisit the question. It said report your answer in scientific notation. Calculator didn't do that. So to write it in scientific notation, we're going to move our decimal point and put it between the 5 and the 6. That way our coefficient is 5.6, and then we count it back. 1, 2. And since our number is less than 1, it's going to have a negative exponent. We're still not done with the answer because there's no units. No naked numbers. Don't let that number be reckless out in these streets. Put some clothes on it. Put a unit on that number. So if you just gave me 0.056, wrong. If you told me scientific notation, still wrong. Now you'll get partial credit, right? You'll get partial credit. But the complete answer is 5.6 times 10 to the minus 2 grams. How did that feel? We're walking through it together, holding hands. How did that feel? Do you feel like you can tackle one of these on your own? Okay. Then here's one for you to try. How many milliliters are in 1.82 liters of water? Report your answer in scientific notation. Remember to start by writing out what the question is. Then write a unit equation that relates the two units in the problem, your unit factors, and then make your decision about which one of those unit factors is going to get you from where you are to where you want to be. I'll give you 3 minutes to get a head start, get it written down in your notebook, and get going. Then we'll start going through it. If you get an answer in that time, go ahead and put it in the chat. Otherwise, don't worry about it. I just want to see how far you got and whether or not you were on the right path. So 3 minutes, that's about 250. I'll give you another minute, but please do try it. And if you get stuck, that's okay. Before we even start going through all of the answers and everything, kind of want to know where everyone got to. So if you get an answer, put it in the chat. Otherwise, tell me where you're getting hung up so we can clarify that for you. Hey, we got an answer. All right. I actually put my arms up like goal, like somebody was gonna see me. I could have kept that quiet, but I shared. So when we get to that part, when we're going over the answer and how to do it, I will highlight how to figure out how many spaces you're moving. So hold on to that question. I will get to it when we answer the problem. So it looks like we got a couple of folks who got to answer. Great. I see we're adding our units. Good. So the first thing we always do is rewrite the question. So what are we doing? We're converting what to what? We're converting liters, which let me be more specific here. Yeah, we'll go over that. So don't you worry. We'll go over that. I'm going to walk you through the whole problem and then I'll highlight that. And if it still doesn't make sense, then we can talk about it again. So the question that we have is 1.82 liters. What is that in milliliters? See, I like that. Y'all help each other out. So we need to write a unit equation that's going to take us from liters to milliliters. If I have 1 liter, and somebody already put it in there, that means that I have 1,000 milliliters. Okay? That should be an equal sign. That's the same thing as saying 1 times 10 to the third milliliters. Now, how do we get there? The liter is bigger than the milliliter. So we're going from a big unit to a small unit. So think about that pizza. If we're dividing it up into slices, 1 pizza is 8 slices. So that's going to be a bigger number. And that corresponds to the exponent being positive. So I know that part was already cleared up a little bit, but I wanted to make sure that I touched on it too. As far as the unit factors are concerned, we're just writing fractions. So for those of you who did not get to an answer, how many folks were able to get to writing the unit factors? That's the people who didn't have a final answer. Did you get to writing unit factors? You can raise your hand or say me. For those of you who did not get to a final answer, did you at least maybe get to writing a unit equation? Okay. So we have a few that were able to, yes. I have a question. That's fine. Yeah, there's two ways to write the unit equation. That's fine. That's fine. There's two ways to do it, and I don't want to always show both ways each time because that can be confusing. So if you get it that way, go for it. My way is not always the best way for everyone. All right. Cool stuff. So we've got two unit factors from our unit equation. Yes. So that is from the chart. So this number here, the chart is going to tell you milli 0.01, and that's equal to 1 times 10 to the minus third. So that's from the chart. What we're doing is taking everything except for this negative sign because we're determining whether or not it should be positive or negative based on how we're writing our unit equation. Is that clear? Okay, great. The last step is your setup. We're going to set up that calculation. We have 1.82 liters, and we need to choose which unit factor is going to cancel the liters and give us milliliters. So of the two that I've written, which one will do that for us, A or B? B, right. You always want to double check, especially if things get more complicated. And we've got the right unit. So now, you don't even have to touch your calculator because the scientific notation is done for you. So that's why I chose to write it this way, because it makes your life a little bit simpler. Now, last class I taught, they asked, is it always going to be this second unit equation that you use? The answer is no. It's just that the problems that I have, that's how it works out. But that's not always what you're going to use. So you need to make the decision every time. Don't just say, oh, well, it's always the second one. Not true. So how do we feel about this one? Shaky, meh, good, empowered? How do we feel? And it's okay if you say shaky. Is there a question? So this is a special case where 1.82 is already at least 1 in between 10, and we're multiplying by 1 times 10 to the third and dividing by 1. So we don't have to do any real calculation there. But if any of those things were different, you would have to do the calculation. So let's say that you did it where you wrote 1,000 milliliters over 1 liter. Then your calculator is going to tell you 1820, and you need to write that in scientific notation. So you'd place your decimal point between the 1 and the 8, and you'd have to know that you're only going to use 3 sig figs, which is what you got from the problem. So the coefficient would be 1.82, and then you move your decimal point 1, 2, 3 times to get it back to where it was. And it's positive because we moved the decimal point from where it was at the end to the left. That's one way to think about it. The other way to think about it is that the number itself, 1,820, is bigger than 1. So your exponent is going to be positive. Does that answer your question? Great. Other questions about this? Because we're getting ready to step it up. All right. Here we go. So we did the metric conversion. We had one unit equation, one unit factor. Now we're doing two metric conversions. So we're going to have two unit equations and two unit factors, or two sets of unit factors that we need to choose from. I'm going to walk you through this one, and then you're going to do the next problem. How many nanoseconds are in 5.21 kiloseconds? Report your answer in scientific notation. It's a theme there. So our question is, we have 5.21 kiloseconds. We're trying to figure out how many nanoseconds that is. Notice how in both of these, there's a prefix. There's no direct relationship between kilo and nano. So you have to use two metric conversions. The first, we're going to go from kiloseconds to seconds. That's going to be our first step. Then we can take those seconds and convert those to nanoseconds. So that's why this is called two metric conversions, because we're literally doing two of them to get from where we are to where we want to be. For our first unit equation, we need to go from kiloseconds to seconds. Kilo, is that bigger or smaller? Right. I feel like one of those kids shows like Dora or something where they ask the question and then they pause and stare at you with those big eyes that are kind of creepy. And then they're like, yeah, that one's the blue square. Like, because of the delay with the internet, that's how I feel. Feels a little bit silly, but hopefully we're good with that. I have to share my thoughts. Y'all have to know I'm human. I think about these things. Anyway, we're going from big to small. That means that when we write our exponent for the smaller number, that exponent is going to be positive. You'll use the chart to figure out what the exponent is, the number, and then you'll figure out the positive negative piece. So it's positive, so we're good there, and we can say 1 kilosecond is equal to 1 times 10 to the third second. You don't have to go through that step of going big and small if it makes sense to you just by looking directly at the chart. If it makes sense to you, do it. Otherwise, if you need something that's a little bit more systematic to make sure that you get it, you can try this method. But there's the big wide world of the internet and YouTube, and there's tons of videos on how to do these types of conversions. So if one of those makes more sense to you, one, share it with me, and two, use it. That is saying that we need to go from seconds to nanoseconds. So that's the second part of the metric conversion. The first part is kiloseconds to seconds, which we're handling now. The second part is going to be converting those seconds to nanoseconds. Okay. So we write out our unit factors. Which look like fractions. Now we have to do this for the other side. I'm going to try to, so I'm going to rewrite this somewhere else because I kind of need all the space. Now we need to write a unit equation that relates seconds and nanoseconds. Nanoseconds are smaller than seconds. So for this one, we're also going from big to small. 1 second is equal to, you look at your chart, you get that 9 from the chart, and big to small, we already said that exponent is going to be positive. So if you have 1 second, you have 1 times 10 to the 9 nanoseconds. Then we write our second set of unit factors. If you're still with me up to this point, let me know. Say you're with me. If you got lost somewhere, come find me. Good. So now we've got all the pieces to put together our calculation. So the first part of the calculation is going to be handling the kiloseconds to the second. We're starting with 5.21 kiloseconds, and we need to make a decision. Which unit factor should we use? if we're trying to get rid of kiloseconds and be left with seconds? A or B? We're going to use B. Just to demonstrate that, we've got kiloseconds in the numerator and the denominator, so we can cancel that out, and we're left with seconds. So we're here. It's like at the mall with that map. You are here. That's where we are. We're at seconds. Now we need to go from seconds to nanoseconds. We've got a second decision to make. Which unit factor are we going to use? A or B? We're going to use B again. I promise you we'll do some where it's not always B. Yes. Yes. Exactly right. You called me just now. I was about to show how you cancel. So you're setting all this up. You're canceling out the seconds now, and you're left with nanoseconds. Now we're ready to touch the calculator. We've set it all up. We know that our units are going to leave us with nanoseconds, which is what we want. So go ahead and try putting that into your calculator and see what you get. Remember, you need to report your answer in scientific notation. Yes. 5.21 times 10 to the 12 nanoseconds. So if you are savvy with your exponents, you don't have to touch your calculator. You can add the 3 plus the 9, and that will give you 1 times 10 to the 12th, and then you just put the 5.21. I think I heard a question about to be asked. Yes. Okay. Yeah. Sometimes we don't remember all the rules with the exponents, so it's easier to make sure that you know how to put it into your calculator. Because even if you do know it, sometimes in a test situation or you're just tired, you make a mistake. So it's always good to be able to check your mental math. Question. So the last time, I can go back to that. So the last time, we only had one thing that we were multiplying by. So that's why I said it's a special case where you just plop the 1.82 in for the 1 and there's your answer. But in this case, we're multiplying by two things. So you can't just replace the 1. You have to first figure out what 1 times 10 to the third times 1 times 10 to the ninth is. And then you can plop in your 5.21. Okay. So how do we feel about that one? Are we ready to tackle one on our own? All right, let's do it. So you have an experiment that you have to do, and it requires 25 picograms of enzyme. How many milligrams of enzyme do you need? Report your answer in scientific notation. So if you do not have that chart, P is pico. I'm not writing out all the zeros. And that is going to be 10 to the minus 12. Milli the chart will tell you 1 times 10 to the minus 3. After we do this one and go over it, then we'll have a break. Shake your brain out. So try this question. We'll go over it. I'll give you 3 minutes head start before I start setting up the question. If you get stuck, take note of where you get stuck, and then you ask your questions. I'm going to start setting up the problem here, but I'm not going to go all the way through to the answer. Just in case some of you are stuck, I'll help you get a little bit unstuck, and then you can try. The question that we have to answer is if we have 25 picograms that we're trying to get, what does that mean in milligrams? There's a prefix for the picograms. We have a prefix, milligrams. So we can't just go directly from one to the other. We have to first convert picograms to grams, and then convert grams to milligrams. Your first unit equation, you're going to write something that tells the relationship between picograms and grams. For your second unit equation, you need to relate grams and milligrams. So I'll give you another minute or two to work on that. Put your answer in the chat if you get one, and then we'll go through it. I'm going to wait and see if we get any more answers, but we've got one. Don't forget your unit. So let's get started with these unit equations and we'll work our way to the answer. Now we got some more answers coming in. Excellent. It seems like whenever I'm like, all right, let's get started, it's like the internet is holding those back. And then I'm like, all right, we have time constraints. And then all the answers flow. Amazing how that works. So we'll move our way through the problem and get to the answer, and then you'll see whether you got it. The first thing we have to do is relate picograms to grams. Picograms are smaller than grams. That means that we're going from a small unit to a big unit. When we move from small to big, our exponent, is that going to be positive or is it going to be negative? It's going to be negative. So if I have 1 picogram, keep writing that doggone arrow. Got arrows on the brain. Then I go to the chart and I just want the number for the exponent. I'm going to use my own logic to figure out whether it should be positive or negative. We said we're going from small to big, so the exponent should indeed be negative, and that's grams. We write our first set of unit factors. So that's the first part. Now we need to talk about the second leg. We need to go from grams to milligrams. In this case, we're going from big to small. So that means our exponent is going to be positive. If I have 1 gram, if I write one more doggone arrow instead of equal sign, I just might pull my hair out. Okay, maybe not. I like my hair too much. Took me too many years to grow it out. Anyway, if I have 1 gram, I look at the chart. I just want the number for the exponent. My exponent needs to be positive, so I'm done. 1 gram is the same as 1 times 10 to the third milligrams, or 1,000 milligrams. Then you write the unit factors. Are we good up to this point? So several of you put in answers, but many of us did not. So did we at least get this far? Even if you didn't share your answer, I just want to know where you got to. Okay. Now we're going in for the final haul. Gonna switch up some colors because this just needs some brightness. So we're starting with 25 picograms. Which unit factor are we going to use from our first set to go from picograms to grams? Why are we using B? What is it about the unit factor in B that makes it different? It cancels out the picograms. Good. It's easy to just choose A or B. We want to make sure that we're doing it for the right reason. Now we need to go from grams to milligrams. So let me show you the cancellation here. We've gotten rid of our picograms. We're at grams. We're again going to use B because the grams are in the bottom and that's what we're trying to get rid of. We cancel those grams out and we're left with milligrams at the end of the day. So what you should get when you report your answer in scientific notation is 2.5 times 10 to the minus 8 milligrams. So how do we feel about that one? Okay, so if you just did the trick of saying, okay, I've got 1 times 10 to the minus 12 and 1 times 10 to the third, that's going to be, just for your exponents, negative 12 plus 3 is we're adding, right? Because it's exponents and we're multiplying. So that gives you negative 9. If you add in your number, 25 times 10 to the minus 9, well, yeah, that's a number, but it's not scientific notation. Why? Because 25 does not fall between 1 and 10. So you have to take that decimal point that is implied at the end of the 25 and move it over one more time so that you get 2.5 times 10 to the minus 8. Yeah, a little bit trickier there. Other questions? Looks like people are good. Did that answer your question? Okay. So yeah, one person said, no, we're not good. Why aren't we good? Oh, okay. I was like, oh no, I thought we were good. So it's fine. I do that to my kids all the time. Stand up, put the thing on the other thing, I could confuse myself, so it's all good. So the -8, if you put it into your calculator, you're going to get an answer with a lot of zeros and then 2 and a 5. You can write that out and then just write it in scientific notation. Or you can do the trick where you do the multiplication of these two numbers first. And when you are multiplying exponents, you're adding the exponents. Okay. Yeah. So there's going to be office hours tomorrow. I'm going to bring that up at the end of class. But since we mentioned it, everybody might not make it to the end. But tomorrow, Wednesday, from 12:30 to 2:30, I will have virtual office hours. So that will help you out if you need more help with Chapter 2, or if you have questions about Chapter 1, you just want to introduce yourself. If you have that somewhere in there free, you can stop on by. I'll post in the announcements on Blackboard what link to go to, how you can meet up with me virtually for office hours. Okay. Because this is a lot of material, so if you missed out on stuff, it's going to be struggle bus. No problem. So that's the 2 metric. We did one where I kind of walked us through, and then I did another one where I let you loose a little bit. Looks like we're feeling better. So even if you didn't get the answer, hopefully I'll get some more of you who didn't necessarily participate yet. Even if you didn't get the answer, do you feel better about these problems than you did before we started? So let me know if you at least feel better. Okay. Because that's what we're working towards. We're working towards feeling better each time we do a problem. We worked through this problem. I promised you a break. So I have 3:33. Let's break. Come on, A. We'll break for 10 minutes. There's a lot of material. So we'll break till, we'll say 3:44. Okay? Shake it out for about 10 minutes, and then we'll get back to it. Alrighty, it's 3:44. So we're going to get back to it because we have quite a bit left to cover. The metric conversions usually take a while. So we have to talk about compound unit problems, and then we'll be on our way to doing some of the other concepts that were covered in Chapter 2. The average low-flow shower head flows 3 gallons of water per minute. What is the flow of water in liters per second? So in this case, we're doing a US metric conversion. And you're missing one key piece of information that I would always provide for you in an exam setting or something like that. And that is, how do you relate gallons to liters? If you Google it, Google will tell you 1 gallon is equal to 3.785 liters. The question, we have 3 gallons per minute, and we want to know what is that in liters per second. So our game plan is a little bit different. We still have to do 2 conversions, but we're converting 2 different units. We have to go from gallons to liters, and we have to go from minutes to seconds. The process is still the same though. We already have a unit equation to go from gallons to liters. That would be provided for you in this kind of a compound unit question. But we still need some unit factors. Are we good so far? This isn't anything new from what we've been doing. Come on back from break, y'all. Shake the cobwebs out. We don't have that much longer to go. I know 2.5 hours is a long time. And I know it's a long time because I wrote 2 instead of 1 there. So these are unit factor set number 1. Now we have to do the same thing to go from minutes to seconds. How many seconds are in 1 minute? Yeah, that's something everybody knows, right? So you're not going to get that information on an exam. You should know 1 day is equal to 24 hours, 1 hour is equal to 60 minutes, and 1 minute is equal to 60 seconds. Those are things you should know just from being alive for more than 8 years of your life, okay? So our unit equation is 1 minute equals 60 seconds. And our unit factors, same as always. Now you see me labeling, so you know what the next step is. We have to set up an equation. We're starting with 3 gallons per minute. Notice how I wrote that as a fraction, and the 3 is in the top, minutes is in the bottom, okay? Our first goal is to get rid of gallons. So am I using A or B for from unit factor set 1 to get rid of gallons? We're going to go with B. It has gallons in the bottom. So now we have liters. But this next step is different from what we've been doing. We have another unit that we want to get rid of. We want to get rid of minutes. Minutes are in the bottom, or the denominator. So which unit factor from set 2 are we going to use, A or B? Yeah, we have to use A because we're trying to get rid of the minutes. And if we have something on the bottom that we're trying to get rid of, we have to put that same unit in the top. So we're not canceling out liters. Instead, let me do a different color here actually. We're getting rid of minutes, and we now have seconds. So our new units are going to be liters per second. When you put this into your calculator, you're going to say 3 times 3.785. Then you're going to divide by 60 because the 60 is in the denominator, and that means you're dividing. So don't forget that. Put that into your calculator and see what you get. Yeah, so our calculator tells us a bunch of numbers, 0.18925. But we have to think about sig figs. The other problems, we didn't think about it because we were just taking one number and moving the decimal point around a bit. So we didn't really do anything to change the number of sig figs. But here, we did. So now we go back to the problem, and the only measurement that we have that we're going to consider is the 3 gallons per minute. There's only one sig fig there, so we can only report one sig fig. So if our calculator answer is 0.18925 with sig figs, we're going to report that as 0.2 liters per second. So it's the same process, but the calculation is a little bit different. Each of the problem types that you've seen, going all the way back to writing the unit equation or writing the unit factors, the different metric conversions, all those things are fair game for the exam, and you will see some kind of representation of all of these problem types that we've done so far. So make sure that you can do them all. If you have questions about this, office hours would be a good place to come because we can do some more problems like this. Otherwise, you can send me a message through course messages on Blackboard, and you can always do extra problems for practice. In the interest of time, we need to move on to the other problem types and the other concepts. Percentages are something that you encounter already. You've been in school for a long while, so you know what a percentage is. We're talking about a part over a whole times 100%. That part over a whole looks a lot like a unit factor. It's a fraction. So if we add units to that part over a whole, we end up with a unit factor. And that's helpful for solving problems. So what I want you to do first, and I know we're switching gears, we have this percentage, 4.70% iron. I want you to write 4.70% iron as a unit factor. And the units that you can use is grams of iron and grams of sample or grams of earth. Try writing it as a unit factor and let me know what you get. Here's the hint that I said in words. Looks very similar to the part over the hole. Any guesses for what I might be putting in the top? If we're trying to say 4.70%, yeah, there we go. So I agree with you with the top part. We've got 4.70 grams of iron, but we're just talking about the percentage. If we have 4.70 grams of iron, the whole is 100 grams, just like 4.70% is like saying 4.7 over 100. So literally what we did was add units, grams of iron, grams of sample, and put it right there. We'll let that simmer for a second, and you let me know if that makes sense. Because we just took a percentage and wrote it as a unit factor. Let me know if you're with me. If you're not with me, that's okay. But in the interest of time, I will move on unless someone asks a question or says, nah, you lost me. So when we're taking the percentage and writing it as a unit factor, this bottom number will always be 100. That's only for the unit factor. And just like with other unit factors, we can flip it and say 100 grams of sample over 4.70 grams of iron. But when you're writing it out initially, it's always going to have the 100 on the bottom. The 71 grams of sample, that's going to help us answer the question. Right now, we're just writing unit factors from our percentage. We haven't even touched the 71 yet. So that's the other unit factor that we can write. Once we get our first one, then we can flip it and write the second one. Now the question is asking, we have 71 grams of sample. What does that mean for iron? How many grams of iron do we have? This is where we set up the equation just like we did with the conversions. We have the grams of sample, and we want to use one of these conversion factors or unit factors to go from grams of sample to grams of iron. So which one do we use, A or B? We're going to use A. See, I told you it's not always B. So to get back to your question, the purpose of the 71 is so that we can figure out the number of grams of iron in that sample. Every sample isn't going to be 100 grams. If it were, it'd make life easy. So we can cancel the grams of sample, and we're left with grams of iron. Just like in the last problem, where there is a number in the denominator, don't forget that you have to divide by 100. So it's 71 times 4.7 divided by 100. Otherwise, your answer is going to make 0 sense. Put that in your calculator. Let me know what you get. Yes. Yeah. Yeah. You never cancel out the numbers. We're just talking about the units. Your calculator is going to tell you a bunch of numbers, as usual. But we need to report the right number of significant figures. And the only significant figures that we have to go from is the percentage, which has 3 sig figs, and the sample, which has 2 sig figs. So I see all of you have put your answer with 2 sig figs, so that's right. When we round, we're going to round that 3. We look to the one next to it, that's another 3. So we're just going to get rid of it and say 3.3 grams of iron. So the key to this problem is taking that percentage and knowing what to do with it. Now in this case, we didn't have to use the other unit factor, but there may be a question where you need to. I didn't want to move on to that just yet. So don't just write this unit factor. Also make sure that you write the second unit factor so that you have both as options. If you're like, okay, I kind of get it, or you get it, then we're going to call that good. I don't think we're going to be able to finish all the way through to the last slide, but don't worry, I'll help you out, okay? Because the specific heat one is also a question that's going to take a little bit of time. So are we good with percentages? Here we go. The next concept is volume. So volume, we're talking about how much space something takes up. And the key here is looking at the units. Volume is always going to be something cubed. If you're trying to convert one unit to another, like in this problem, we have centimeters cubed, and we're trying to go to meters cubed. Another way to write centimeters cubed is like that. And we're trying to go to meters times meters times meters. So that's what that conversion looks like. For this problem, we have the volume of a Rubik's Cube, which I don't even know if people know what that is anymore. It's popular in the 80s. The approximate volume of a Rubik's Cube is 185.2 centimeters cubed. We need to write that volume in meters cubed. We still need to write some kind of an equality or a unit equation. I teach multiple chemistry courses. They use different terminology for the same thing, so I try to be consistent with the textbook. But if I say one and I'm like, oh wait, the other, it's because I'm mixing the terminology. They're the same. So I apologize. I hope that's not too confusing. In your textbook, you're using unit equations. So we need to write a unit equation for how to go from centimeters to meters. And we've done this before. We've done this example a couple of times. We know that centimeters, maybe we haven't done it enough because I was about to write the wrong thing. All right. Centimeters are smaller than meters. So that means we're going from small to big. In terms of our exponent, that exponent is going to be negative. So if I have 1 centimeter, that's going to be the same as having 1 times 10 to the minus 2 meters. Haven't done anything different. We've written that one before. From there, you can write unit factors. But here's where things go a little bit differently. We still need to set up the problem, and we still need to decide which unit factor to use. But instead of multiplying once, we have to use that same unit factor 3 times, because we have to cancel out centimeters 3 times to get to meters cubed. So remember how I wrote up here, centimeters cubed is centimeters times centimeters times centimeters. We need to cancel out each of those and replace it with meters. Which unit factor am I going to use to get rid of centimeters? Right. And you're going to do that 3 times. Now in your book, they may cross it out with like multiple different colors. We'll try to replicate something like that. I hope nobody is red, green, colorblind, because I've got limited options. So we get rid of all those centimeters cubed, and we end up with meters cubed. Because when we multiply the numbers, we're also multiplying the units, meters times meters times meters. Try putting that into your calculator and see what you get. I like that you're writing it in scientific notation. Your calculator is going to tell you this. You need to, now it doesn't specify in the problem to use scientific notation, but chances are if this were a multiple choice question, all the choices would be in scientific notation. And don't forget that meters cubed. So that's the concept of volume. Any questions about that? All right. Now we're going to get to density, and I think that's probably where we're going to have to chop it. I will post the rest of the stuff about specific heats and heat versus temperature. Ask me questions about it, because the specific heat one is really the only one that might trip you up. The other parts are pretty easy concepts to get. We're not covering specifically how to do the temperature conversions. I think that those are simple enough to where you can get it. If you have Fahrenheit and you need to get to Celsius, you choose the right equation. Okay. But if you need help with that, that's what office hours are for. So we're going to go through this concept of density, and then I'm going to go to the last slide to give you some reminders. And then class will be over. So I'm going to first introduce the concept of density. We're just taking a mass and dividing it by a volume. The different units that you can see for that are just different ways of representing volume. For a solid, you're going to see grams per centimeter cubed. For a liquid, you'll see grams per mil, or milliliter. For gases, it's grams per liter. This question, we're talking about a solid. The density of green jade is 3.33 grams per centimeter cubed. And this was a typo, it should be like that. Okay. A sample of green jade placed in water causes a displacement of 8 milliliters. What is the mass of the sample? This idea of volume by displacement is pretty simple. Everyone in their life has taken a bath. You run the bath water, you plug up the tub, you run the bath water, you sit in it. Maybe you don't do that anymore, but when you were a kid, you were probably in the bathtub playing with your toys because your mama needed a break and she knew you weren't going to die. Okay? When you sit down in that bathtub, you see the level of the water increase. It may not be a lot, but that level goes up. So the apparent volume of the water increases. It's the same idea with volume by displacement. Initially, there were 30 milliliters of water in this graduated cylinder. You put your sample in, and now all of a sudden you have 38 milliliters of water. You didn't gain more water, but you put something into the water that displaced it so that now the level is reading higher. The difference between the final volume and the initial volume will tell you what the volume of your sample is. So that is 8.0 milliliters. That's how we got the volume. I'm going to replace this with 8.0. Does that concept make sense? Volume by displacement? Okay, good. Now we can address the problem itself. We have the density of green jays. We know the volume, but we don't know the mass. Just like percentages, we can use the density as a unit factor. So 3.33 grams per centimeter cubed, we can rewrite it like this, and we can flip it. When you flip it, you need to have a number in the top. It's just an implied 1. So we can actually write that there. So that's density as a unit factor. We didn't do any calculations yet. We're just taking the information that we have and making it more usable. Because once we have a unit factor, we can convert from volume to mass. We're starting with a volume of 8.0 milliliters. Milliliters is the same thing as centimeters cubed. So we'll just write centimeters cubed for clarity. They're the same thing. 1 centimeter cubed is equal to 1 milliliter. We now need to choose a unit factor to go from centimeters cubed to grams. That means we're going to choose the one that has centimeters cubed in the bottom. Yes. It's just because it looks like it won't cancel. Our density is 3.33 grams per centimeter cubed. The volume, you were told 8.0 milliliters. It's the same thing. So if I wrote milliliters there, it would look weird to cross it out. Yes, 1 centimeter cubed is equal to 1 milliliter. That comes from the definition of what a liter is. So this you can take to the bank. I don't know what they're going to do with it there, but that's a saying. All right. So when we do this calculation, we're going to get rid of the centimeters cubed, and we're going to end up with an answer in grams. Your calculator will tell you 26.64. However, we can only use 2 sig figs because that's what we have for our volume. So we round to 27 grams. I know we went through that a little bit fast. That's the last concept that we're really going to be able to get through. If you have questions about that, now is a good time. And then I'm going to go to the end of this presentation to give you some reminders. And we'll do some modifications for the homework, probably for both of the sections, just because the specific heat, it's a little bit of an in-depth kind of a problem, and I want to make sure that you actually get it. So are there questions on density? Okay. No. So I didn't write an equal sign between the milliliters and the liters. That's different. What I'm saying is grams per centimeter cubed is the same as grams per milliliter. This one is all by its lonesome. So good. I'm glad you asked that. All right. If there are no other questions, the last concept was specific heat. We don't have time to do the whole problem that I have after this, but I can at least break down the different pieces of the equation and make sure that you understand it. And then we can go to the very end. Specific heat tells you how much energy you need to take 1 gram of something and increase its temperature by 1 degree. So if I have 1 gram of water, and it's at 37 degrees Celsius, if I want to bump it up to 38 degrees Celsius, the amount of heat required to go from 37 to 38, that amount of energy, that's the specific heat. You can calculate the specific heat of any substance if you have 3 things. 1, you have the amount of heat, which is just energy. And the SI unit for energy is joules. You also need to know a mass. So oftentimes, the question will say something about, you have a flask and it's sitting in water. It's in a water bath. and it tells you, okay, X amount of heat is being deposited into the water from the reaction. You need to know the mass of the water because that's the specific heat that you're going to have. The last thing that you need to know is the change in temperature. So that's what this delta sign is. Delta means change. Shoot. I don't know what just happened there, but it looked like everybody got kicked off. Are we back? It looks like it. I don't know what happened. Okay, so it says it's reconnecting. By the time it reconnects, class is going to be over. So don't worry about it. Specific heat, we didn't get to it. I will go over it. I'll finish out the notes and post the completed notes. But what I do want to focus on is your homework and the first exam. So your Mastering Chemistry homework and quiz for Chapter 2, along with the check-in, are due on Sunday. So if you can you still hear me at least? Because the screen sharing, I don't know why, but it always takes 9 years to reconnect. So by the time it does, class is going to be over. So you have homework due September 6th. I have office hours. So what's due on Sunday? Mastering Chemistry. You've got homework and a quiz. There's also the Chapter 2 check-in. All of that is due on Sunday. I have office hours on Wednesday, tomorrow, from 12:30 to 2:30 p.m. I will post an announcement that tells you how you can access me virtually for office hours. I haven't decided whether it's going to be Zoom or Collaborate. Either way, you will have access to me from 12:30 to 2:30. So I recommend that you at least look over the homework problems, even if you don't do them all, and see which ones you're like, that's kind of shaky. So you can have something to bring to me tomorrow. Your first exam is going to cover the prerequisite science skills and Chapter 2. We're not going to lean too heavy on the specific heat, which is the last concept that we didn't get to cover. I wanted to go over it just because it shows up in some of the homework. The first exam will be available from September 9th at 8 a.m. to Friday, September 11th. So Wednesday through Friday, you choose a time to do your exam on Blackboard. Before then, make sure that you've tried that practice exam that I've posted so that you can make sure your computer is compatible with Respondus, the lockdown browser and monitor. It's not a real test. It's just a get to know you type of thing. Tell me which option for office hours works best for you, what your major is, what year you are. That's it. Easiest test you'll ever take. Do that before you try to take the exam. Yes. It should be okay. As long as you don't have a lot of craziness going on, it should be fine. So if you are trying to open it up in a new window or something like that, you can't. And you need to open up the lockdown browser and navigate to Blackboard through the lockdown browser. You can't just open up Firefox and do it. You need to open up the lockdown browser. It's an internet browser. You go to Blackboard through that and then open the exam. You're welcome. So I will be posting an exam review, and I'll also put up a PDF of all the solutions worked out. If you have questions, then you can send me a message through course messages, stop by office hours. You can request an appointment with me, and we're going to have some time in the next class next week to do a little bit of a review. Now, that's right before your exam is available, but it's better than nothing. So make sure that before we meet next time, you'll still need to look at Chapter 3, but if you have questions about the previous two chapters, bring those with you. That's all I have for you. Yeah, go ahead with questions, but if you don't have questions, you can leave. It's just, well, it's prerequisite science skills, which is not Chapter 1. So it's the prerequisite and Chapter 2. Chapter 3 is not included on the first exam, but we still have to continue to cover material. So it's a little bit of a bummer because we've got so few class periods together, but we'll try to do the best we can and give you some review before the exam. If there's no other questions, go on ahead, enjoy the rest of your day. Thanks, you too.